Record. Okay, we're going to start out with something and come back to it. I define something called index of refraction. You may also have heard of this as refractive index by the equation N, index of refraction, equals C divided by V. C is a constant, 3 times 10 to the 8th meters per second. This is the speed of light in a vacuum. C is the speed of light in a vacuum. It is the fastest that anything with matter or energy can go. But you don't have to travel at the speed of light in a vacuum if you're light. You can also travel slower than that. For instance, as light goes from air into water, it slows down a bit. If I recall correctly, oh God, what is it? It's like 2/3 the speed in water as it is in air. Air versus vacuum is like 1.00026 or something like that. It's a very tiny effect. It is big enough to make mirages a thing. We'll talk about mirages if we've got time. Mirages are a factor where index of refraction in air is noticeable. Well, we'll get to that. Okay, but for most purposes, index of refraction of air is so close to 1 that we don't care. Plastic, you can have big indices of refraction. I think in lab you have an index of refraction even of 1.7 if I recall correctly, but I'm not sure of that. Don't quote me. Don't steal that value. Test it for the lab, find out. There are materials been made with index of refraction into the hundreds or even higher. I'm not an optics guy. I'm not sure of that, but I'm pretty darn sure. Suppose you've got an index of refraction coming from a material that speed of light in that medium is V is half as great as in free space. V is half of the speed of light in free space. Google question A, tell me the index of refraction N. Again, the question is, suppose I slow my light down by 50%. What is the index of refraction? Google question A. If my speed in a medium is half of my speed in free space, plug into the equation and solve for n, which is already solved for, so I don't know why I said solve for. And I'm looking for a number. It is a raw number. I'm not asking for doubled halved. Again, my question is, if you plug in v is 1/2 of the speed of light in free space, which is this number, what does n work out to be? You may use a calculator if you need. Okay. If v is 1/2 of c, and c is 3 times 10 to the 8th, what's v? 1/2 of 3 is 1.5. 1/2 of 300 million is 1.5 million, yeah? No, you don't like this. Google form B, ask me a question. Because only about 20% of you got this right. So 80% of you are missing something here. Ask me a question. Where'd I lose you? Oh, people are trickling in. Okay. Still, less than half of you got this right. So there've got to be questions going on here. I define C as the speed of light in a vacuum. That's what I wrote. That's the 3 times 10 to the 8th meters per second. And well, yes, Sammy, we are finding n, but half of the class missed it, so I'm trying to build up to that one piece at a time. Say that again, Brendan? Sorry. Okay, so I am asking to plug into an equation, n equals c divided by v, where c is a constant, 300 million, and I'm telling you how much v is. I said that v is half as great as c. V is half as great as c. There was another question about the exponent halving or not. What does 3 times 10 to the 8th even mean? 3 times 10 to the 8th goes by the pedestrian name of 300 million. There are 8 zeros. I am multiplying 3 by 10 times 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 10. Right? There are 10 to the 8th. Okay. When I divide this number in 2, if I divide this number by 2, is half of this number that? No. Half of 300 million is not 150,000. Half of 300 million is 150 million, right? So the exponent cannot also change. If I divide 3 times 10 to the 8th by 2, it does not become 1.5 10 to the 4th. You can also express this by saying, if I'm dividing any a times b by c, this is not equal to a divided by c times b divided by c. You're only dividing by c once, not twice. So half of 300 million is 150 million. Now let me ask you, can you Google Form C, please? What is the index of refraction when light slows down by 50%? Kim, yes. Gerardo, I'm making this up. I am telling you the V, and you can plug into the equation to find N. Okay. Let's have everyone. Again, I'm asking for index of refraction if light slows down by half. Please note, if your final answer is bigger than the universal speed limit 3 times 10 to the 8th, you have made a mistake. Okay, we're at 80% of the class. Let's plug in. 300 million is C divided by 150 million. Let's take a rough guess for how big this number might be. Do you think this number is bigger or smaller than a million? If I take 300 million things and divide them into 150 million buckets, will each bucket contain more or less than a million things? Again, there are 150 million buckets and 300 million things. How many things in each bucket? Well, I can simplify this a little bit by canceling a bunch of zeros. 300 million divided by 150 million is the same thing as 30/15. If I have 30 things in 15 buckets, how many things in each bucket? It's 2. We're at 80%, but I'd really like everybody to be able to do this. Please note, if you have a calculator and you type 3 times 10, 8, divide 1.5, 10, 8, order of operations says multiplication and division are the same operation. We go from left to right. This will calculate 3 times 10 to the 8th. This will divide the answer by 1.5, and then it will multiply by another factor of 10 to the 8th. If you type this into your calculator, you will get 2 times 10 to the 16. As I said at the beginning of class, you can make an index of refraction of, I don't know, several hundred maybe. That's impressive. Not 10 to the 16. That's probably bigger than an index of refraction has ever been made. Follow-up question. In some medium, light travels at 10% of the speed in free space. Find the index of refraction. Light slows down by 90%. It's only traveling 1/10 as fast. What is the index of refraction? Google question D is, suppose I've got some medium that light slows down to 30 million meters per second. That is, say, 10% of free space light speed. It slows down by 90%. What is the index of refraction for that medium? Light is 1/10 as fast in that medium. You may use your calculator if you need. Reflection is not a refraction. Light can travel through to any distance. It is telling how much light slows, but light will not stop. I mean, there's going to be some absorption in any medium. So I guess you have an infinite thickness of glass. 1,000 miles of glass, now light is going to get absorbed by the glass molecules in there somewhere. But if it were perfectly transparent glass, index of refraction tells the slowdown factor. By what factor has it slowed down, which will end up being the degree to which it bends. Bigger index of refraction is bending the light bigger. Okay, I've got some people asking what. Again, my question is, suppose the index of, find the index of refraction if light travels 1/10 as fast, 10% of the free space light speed. In free space, 300 million meters per second. In this medium, 30 million meters per second. Solve for n. You tell me. You tell me. Use the equation. Plug into the equation. Okay, let's plug into the equation here. What is C? $300 million meters per second. What is V? C divided by V. If I have 300 million things and I divide them into 30 million pieces, does it make sense that there would be billions and billions of pieces in each bucket? If you got 10 to the 17, no, reflect on this. If you take 300 million things and divide them into buckets, those buckets do not contain more than the original number of things. What we can do is we can cross out zeros on top and bottom. 1,000,000 divided by 1,000 is the same thing as 1,000 divided by 1. 8 billion divided by 1,000,000 is the same thing as 1,000,000 divided by 1,000. 300 million divided by 30 million is the same thing as 300 divided by 30. So 300 divided by 30. Well, I can also cross out a zero here. 30 divided by 3. What's 30 divided by 3? 10. If you put this into your calculator, What I said a minute ago was I've still got a fair number of people getting billions and billions. In your denominator, put parentheses around two things. 3 times 10 to the 7 needs to have parentheses around it when it's downstairs. Otherwise, your calculator will interpret this as divided by 3, multiply the result by 10 to the 7. Okay, we're going to come back to this because I'd really like this to be a solid skill for everybody. But this is not the entirety of the class, so let's introduce reflection and refraction. For the past 2 weeks, we've studied waves. Now we're going to be going into something called geometric optics. Geometric optics is, can you draw straight lines? Use a straight edge. Use a piece of paper, use a book, use a calculator case, not a curved calculator case, and you'll be fine. We're going to deal with the simplest of geometries here. There is one trigonometric equation, mea culpa, mea maxima culpa. I cannot avoid it completely. I do want to point out that geometric optics and what we have been doing, wave optics, are complementary approaches, that the phenomena we have been dealing with waves and the phenomena we will deal with rays, the ray picture, it's not that one is right and one is wrong. They're both wrong. One is useful in some circumstances and the other is useful in other circumstances. You want to know what light really is? 1, ask me after class. 2, take a freaking number, because physicists have been discovering new answers to that question constantly over the past 500 years. Here is the basic principle of geometric optics. Light is heterosexual. I do that pun all the time, I'm sorry. Light travels in straight lines unless reflected or refracted. Reflection means I turn not entering a new medium. Refraction means I turn when I enter a new medium. Again, the words look very similar. Distinguish from them or you will fail. Reflect, bouncing off of, not entering the new medium. Refract, bouncing, not bouncing off of, entering a new medium and turning. Sure, absolutely. Okay, you can have both at the same time too. Think of the following. I walk by a building at sundown, a glass building. You can see the sun reflected in the glass, right? The people on the inside of the building, do they also see the sun through the glass? Yeah, right? If you're inside a window, you can see the sun through it. If you're outside the window, you can also see the sun reflecting off. There's reflection and refraction at the same interface. There are ways, which we will talk about, that you can get things to do entire reflection. That's the last slide of today. Total internal reflection is the thing. We'll get there. Did I answer your question? Okay, reflection is super easy, although finding images, we'll talk about in a second, may or may not be easy. Here is the fundamental principle of reflection. Angles are equal. Bang. Okay, that's not hard. But I do want to take the opportunity to point out the vocabulary here. What's an incidence? What's incident? Something that happens, right? Uh-oh, I tripped and fell over the ladder. I better file an incident report. No, not that kind of incident. Incident in optics has nothing to do with thing that happens. An incident in optics is an incoming, initial, beginning ray. So the angle of incidence, question? The reflection is when a wave, doesn't have to be light, when a wave bounces off of some new medium and returns to the original medium. Doesn't enter. Yeah, first line. Angle of reflection, it bounces off at equal angles. The bounce angle is equal to the send-in angle. Yeah, so here's a mirror, right? You send light in along this path, boing, it bounces off on that path. And the angle that it bounces back at, the reflection angle, the angle of reflection, is equal to the angle of incidence. So if I shine a light directly straight into a mirror, it bounces straight back. Exactly. Exactly. What happens if you skim a mirror? If I shoot a photon in a ray of light, skimming a mirror, it'll shoot back out at a shallow angle as well. Shoot in at 45 degrees, go out at 45 degrees. It's exactly what you'd expect if you're used to playing billiards or pool, right? Or bullets. I don't know. People who know something about guns probably know not to shoot the ground directly beneath them, or the ceiling directly above them, or the wall directly in front of them. At least people who know things about guns and stay living probably know not to shoot a bullet straight into a reflective surface. Okay, so reflection, easy peasy, lemon squeezy. I do want to emphasize, though, there is one other thing besides terminology. How do we measure angles in all of optics? Mirrors, lenses, anything. We measure angles not with respect to the surface, but with respect to the perpendicular. So, for me, the word steep means big angle, like 90. The word shallow means small angle, like 0, like 1. 1 degree, shallow angle. Is this, here's my mirror, I'm a light ray, pew, is this steep or shallow? No, let me make it more intense. Is this steep or shallow? This is a steep angle. This is a steep angle. This is the shallowest possible angle, yeah? The angle is small if you are almost heading directly into the mirror. The steepest possible, 90 degrees, means you're skimming the surface. I'm just barely coming in because 90 degrees is measured, angle is measured relative to the perpendicular, what I also call the normal line. Draw a perpendicular where the light touches. We measure the angle. This would be like a 30-degree angle here. I'm measuring the angle of incidence is like 30 degrees relative to that perpendicular. Good with the terminology? Now let's do some, no, sorry, one more thing, and then some fun stuff and some fun thinking. Okay, so diffuse, and I didn't write down the other term, diffuse versus specular. I will not test you on this, but you will see references to this if you are looking things up, if you are reading things, and I will talk about it in these terms, so you should know the term, even if you do not need to make a flashcard of it. Also, they're great Scrabble words. Diffuse versus specular. Hey, Cerny, you're looking very specular today. Told my wife this morning. She was reflecting. Just kidding. Two kinds of reflection. Rough surfaces have diffuse, smooth surfaces have specular reflection. Specular means mirror-like. Diffuse means not mirror-like. Diffuse reflections are, take a flashlight, shine it at this ground. Right? Is this a mirror surface in here? Is this carpet polished smooth? If I have a flashlight here, let me do this. Let me conduct the experiment. We will carry out the experiment. Here. Can you guys see that spot of light? Heck, we don't need to do the mirror. Here. This wall. Is this diffuse or specular? Can you see the light? The fact that you all can see the light shows that this is diffuse. The fact that there is an angle which goes from this spot of light out to y'all's eyes, out to y'all's eyes, out to y'all's eyes, that you all can see the light, saying that we've got incoming light going in, striking the surface, and going out at every angle. David, can you see your face right now? How about now? No? Oh, hey, it's on. Can you see your face in the off screen? Okay. Can you see his face? Can you see his face? Can anybody but people sitting directly behind David see David's face? This is a mirror-ish surface. This is specular reflection. Specular reflection, light goes at an angle in and bounces off at that same angle back. The surface is not rough. The surface does not bounce in every which way. That is the angle of reflection that we'd be talking about. Diffuse reflection is how you see each other. Light is reflecting off of, you guys aren't emitting the light. Light is coming in from the lamps, bouncing around the room, bouncing off of your cheek and into your neighbor's eye. Doesn't matter where your neighbor is sitting, right? What we're going to analyze now is where can you see a candle in a bathroom mirror with specular reflection? And in this, you're only going to see it at one particular place. Let's see the physics do this. Wait, sorry. I keep forgetting which slides I put in which order. One more vocabulary lesson here. Real, virtual, and image. A real ray, there's light there. A virtual ray, there appears to be light there. An image is where rays diverge from, either real or virtual. For mirrors, they're going to be virtual rays. So, we're going to learn our first rules of ray tracing. A real is an actual path from a source of light to an observer. A virtual ray, there's no light there. It goes straight backwards from the real observed ray. The image is where the rays appear to come from. Do you guys all know the word diverge? Spread out from, emanate from, come from. Where rays appear to emit from, that's an image. Good? Let's see this in action. Here's how to see David in the mirror. Okay, not David. David's a terrible example because not all of you have seen David in the mirror. But I'm going to imagine that you have all seen a candle in the mirror. Wait, candle? Which century is this? But optics was discovered long ago, so we're going to do it with candles. This is the traditional example. Here is a mirror. Here is a light source. Now, light is emitted in every direction. Very importantly, by the way, did you all know that light goes in every which way from a light source? I talked about that before. Light goes in every which way from a light source. We are only going to focus, pun not intended that time, we're only going to focus on light coming at a couple of angles because it's hell to draw all the impossible, all the infinite number of angles. Come on. There you go. Now I'm freehanding this, so don't blame me if this doesn't line up perfectly. But this should be darn close. Okay. Draw a bunch of angle of incidence equals angle of reflection rays. My bounce angle, bounce angle should be equals to my incoming angle. If you are a candle and you look directly into a mirror, bing, you see light emitted by yourself along that line, right? Your image appears to be along that line. Let's draw a little dotted line to indicate which way candle thinks that light is coming from. You never look into a perfect mirror and think, hey, the light is turned, right? No one ever sees that. We see light as apparently coming straight from an object to us. So the candle sees somewhere along that line is my reflection. Now let's trace back the other. Come on. And I'm freehanding this, so don't blame me. These aren't perfect. Those are roughly straight lines. Oh, that one is actually really crap. Let's redraw that one. Come on. Okay, I mostly did that right. Good. Where does the image appear to be? Bang! There is the candle image. The object, the image, the mirror. Let's do a little bit of geometry. Think about this. Where is the image relative to the object? If those angles are all equal, shoop-a-doop, this is a vertical angle with that, shoop-a-doop. And let's see, that angle is equal to that angle is equal to that angle. Well, these are different angles. That angle is equal to that angle is equal to that angle. Those are all. So if I look at this angle here, I could say that this side length ratio and that side length, wait, hold on, no, I don't want to do that. I want to do the cosine. That side length ratio equals to that side length ratio. Holy crap, there's a very simple pattern here. This length is equal to this length, right? How far into the mirror is our image? The same distance that you stand in front of the mirror, right? You see that? Okay, suppose this is 5 inches from here to here. I put a candle 5 inches away from the mirror surface. Where is the image? What is this distance? 5 inches. This confused my 3 o'clock class. So let me ask for 2 volunteers real fast. Can I volunteer you? Can I volunteer you? You should come forth for a second. Can she come forth for a second? Okay. I will be a mirror. Okay. Come stand on opposite sides of me. I am a mirror plane. Oh, you okay? Okay. Now, are they appropriate distances from each other? Hey, why don't you do some mirroring things? Stick out your right hand. She sticks out her, well, mirrored hand. Yeah, yeah. Put your other hand on your nose. Right. This is just for fun and to mess with them. Okay, right? Now you see they're images of each other, right? How far am I from Jameson? Roughly. How far are we apart? Okay, now step back. Take another step. How far back do you go? How far are they from each other? Twice the distance that either is from the mirror, right? Okay, thank you very much. Thank you. Good job. Google form. First off, tell me, question E, where is the image in a flat mirror? Flat, planar, plane mirror. The image, the reflection, where is that relative to the object in the mirror? You don't have to type the whole darn thing out. This is choice A, B, C, D. This is E, not F, please. Wow, that's a lot of different choices. For the image to be at the same place as the object means that your classmates would have had to stand on top of each other. If you're looking at your reflection in the bathroom, can you see the reflection in the room with you? Is the reflection in the room with you? No, the reflection is in that magical other room that looks just like your bathroom that's separated by that thin sheet of glass, right? Right? The correct answer here is behind the mirror. If the object and the image were at the same location, That would be scary. A is not correct. Likewise, D is not correct. The image, oh, good. This time, nobody. Holy, no, okay. Well, a couple people put D. Fewer people put D than the 3 o'clock. In front of the mirror is to say that it's in the room with you, right? You do not see your reflection on the real world side of the mirror. The reflection is in the other room on the separated by that thin sheet of glass from you. At the surface of the mirror, take a look. Did we locate dot I for image along that mirror? No. The image is not at the surface of the mirror. The image forms behind the mirror, as we said, an equal distance into the mirror. Question F, Google form. Question F. I stand 12 feet from a mirror. How far am I from the image? Google form F. I stand 12 feet from a mirror. How far am I from my image? I stand 12 feet from a mirror. How far am I from my image? Better than the 3 o'clock. Good. 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 Not 144 feet. You're fired. How far were your classmates from each other just earlier? Were they the same distance as they were from the mirror? They were twice as far from each other. If the object distance is equal to the image distance, distances are relative to the mirror. If they are the same distance from the mirror, then they are twice as far as that distance from each other. Correct answer is 24 feet. Okay. Okay. Before we do this one, which also many people struggle with, Google form, talk to your classmates for 2 seconds, refresh what we've just done, and Google form me a question in G. Tell me where you're struggling with reflection and images and mirrors. I didn't ask if there's anybody that can't see themselves in a mirror. That would be useful information. If you are a vampire, you are disadvantaged in this class through no fault in your own and would be excused from this module. Do not wish to be ignorant of a vampire disability. Mackenzie, good question. The dotted rays in the diagram are virtual rays. Exactly what I was intending to do that. Yes, but only yours, Marcos. Ryan, womp womp. Ricardo, distance from mirror is the same as the distance that the image is behind the mirror. That is vitally important in being able to say that the image is 24 feet away from the object. Optometry students are bored. Yep, got it. Will it be on the final? Yep, you betcha. The mirror, question. Okay, the mirror object is 12 feet away. As I stated, if the object is 12 feet away from the mirror, how far is the object from the image? Let's sketch it. As we just did, the distance that the object is from the mirror is the same as the distance that the image is from the mirror. If that's 12 feet and that's 12 feet, how far is object and image? 12 plus 12 is 24. So the mirror is 12 feet from the object. The image is 12 feet from the mirror. Distance from the object to the mirror is 24. If the image seen in a plane mirror cannot be in front of the mirror, how can it be behind the mirror? Okay, so here is the mirror world. Here's you. Here's your toilet. Here's your bathtub. Like anyone can afford bathtubs these days. Here's the door. So here's your bathroom, right? Your bathroom mirror. Wait, there's a sink, right? Sink. Here's the sink. tap. Presumably the sink is on a vanity, whatever. Okay, so here's the real world. Here are you. Where is that gorgeous stranger, that jaw-droppingly stunning stranger? If the jaw-droppingly stunning stranger is here, I call that in front of the mirror. In front of meaning on my side of the mirror. But no, as much as I have tried, and I can neither confirm nor deny that I try daily just in case, you cannot pass into the mirror. This is behind the mirror over there. So if I am talking about where is the object is on the other side of the looking glass, Alice. Behind the mirror is in that virtual realm where we see our images. So if you are looking at the image of an image, what would that be? 4 times the distance? It would also depend on the distance of the image. Yeah. Yeah. How far are they apart? If the mirrors are 6 inches apart or whatever, then the reflection of the mirror, the next one would appear to be 24 inches away. Each surface, the separation between those reflected images would seem to be, I think I'm doing that right, 24 inches. Yeah, do that geometry. It's a fun exercise. Stick around after class and ask me. That's, I suspect, going to wreck many people's brains. Stick around and we can play with that geometry a bit. So a mirror is not a piece of glass. A mirror is metal that is very flat. The piece of glass is just there to support the metal. If you touch the glass, your finger is not on the reflecting surface. You can measure how thick the glass is by the distance that your finger appears to touch mirror finger. Next question, is the imaginary line behind the mirror the virtual rays? Yes. Okay. Again, if the image seen, I want to make sure that everyone understands this. If the image seen in a plane mirror is not in front of the mirror, how can it be behind the mirror? I'm not claiming that there is a stranger in Wonderland in the looking glass. I am saying the location from which lots of observers seem to see a candle is back there, inside the mirror. I'm not saying that there is a thing there. I'm saying that there is an image there, a reflection, a place from which the light appears to emanate. That's what we see when we look at reflections. Okay. No, here we go. An object is located near a small mirror. Here is a brain teaser. I'm going to scaffold this in 2 parts. Here is a mirror, a small mirror, a finite mirror, not an infinite plane not an infinite plane that you could see things at any angle. I'm going to place an object here. Here's my object. It is a candle. Let me move these closer. My first question is, where is the image? Is the image here? Is the image here? Is the image here? Is the image here? Here, image here. I'm going to ask momentarily where you can see the candle flame. So we got to name these. Real world places A, B, C, D, E, F, G, H, I, J, K, L. Ah, hell. Why not? M, N, O. Okay, so the real world places, A through F. And then there are lots of places behind the mirror, G through O. Your first question is, if the object location is at point C, where is the image location At what letter or letters is the image formed in the mirror? Google Form H, tell me, where is the image? From anybody's perspective. The image location does not depend on perspective. There is one place in the universe from which, looking into the mirror, you see a candle. Okay, let's step back a second. Let's take a look at the previous picture and identify a pattern here. What do we say? If you're 5 inches in front of a mirror, candle appears to be 5 inches behind the mirror. Along what line is candle? If I form a perpendicular line, if I form a line at right angles to the mirror, right, there's a candle along that line. So the correct answer, the one and only correct answer here is at point K. That's the image. That is the image location. Follow-up question, where is the candle visible from in the real world? If I stand at A, can I see the reflection? If I stand at B, can I see the reflection? If I stand at F, can I see the reflection? These are supposed to be, this is supposed to be on my iPad. I was trying to draw a 1-inch grid, by the way. So the horizontal and vertical distances between each point is supposed to be 1. The mirror is supposed to be 1.5 units long, if that helps. So Google Form I, at which location or locations could you stand and see the reflection, the image of the candle in the mirror? If you are a fey creature and are capable of entering mirrors, God, this module will be harder for you. Fey creatures and vampires would really struggle with physics. Or maybe if you're struggling with physics, that means you're a fey creature and or vampire. Anyway, moving on. Let's see what people answered. Again, we're asking where in the real world could you stand? I will point out that any letter above F is not in the real world. Okay, let's form lines which extend along various lines of sight. If I am standing at point A looking at image at point K, does that pass through mirror? Form the line, dudes. Does the line from A to I pass through the mirror? No, there's nothing to make a reflection there. Does the line from B to I pass through the mirror? No, there is nothing to make a reflection along the plane at that point. Can the candle see himself? Yes, there is a path that goes. Ultimately, what is really happening is there's the path that goes from candle to mirror and straight back. If we extend that back, the virtual ray inside the mirror goes straight to the image. Can a point at D? So yes, C can see himself. If I stand at D, there is a line which goes directly from the image through the mirror surface. What's actually happening is that there's a ray bouncing off, ping, ping, and going to point D. Yes, D can see the candle. Well, D can see the candle. You can all see the candle. D can also see the reflection. Point E Ping, ping, yes. But look, E, there's a reflection where there needs to be when I pass from mirror world to real world. Point F, no way, Josue. There is no mirror here reflecting. So the correct answer is CDE. Now, let me be a YouTuber and ask a follow-up question. If I hold up a pillow blocking my sight of myself, I'm going to go to a mirror, I'm going to hold up a pillow, I can no longer see myself. The Google form question is, can anybody else see me? If I am C and I'm holding up that green pillow, can anybody see me? And if so, which points? Pointer points. Again, I make a pillow, I put a pillow in front of a mirror, blocking my sight from the mirror. Yeah. Well, yeah, well, of course everyone can see me. Can they see my image? Can they see me reflected in the mirror? Yeah, unless there's like walls here and here, of course they could see you directly. I'm talking about the reflection. I can't see my reflection. Does the mirror know I'm there? I does I is no. The only real world points are A through F. The possible choices are A through F, or none, or all. Okay. So again, go home and try this. Take a friend into the bathroom with you, probably at home, not in a public bathroom if they're of the opposite sex, or of a different sex, I should say. Hold a pillow in front of your face. Look into the mirror. You can't see yourself. Can they still see you is the question. The answer is yes. If you block the light path directly from you to the mirror, you have not blocked these rays. You have not blocked these rays at all. D and E can still see you perfectly well. This is a YouTube video, by the way. Somebody is astonished to find out that despite the fact she can't see her reflection, other people still can. Obviously, she never had my class. Follow-up to the follow-up to the follow-up. Last question about mirrors, and then we're moving on. We're really moving on because we're low on time. Suppose I have a very small mirror now. Here's the mirror. The straight line path from C to I does not pass through straight line. Okay. Google question. If I have a very small mirror as shown in black, can anyone see me in the mirror? Do I have any reflections? So not just holding up a pillow, but like making the mirror smaller. Can anyone see me in the mirror? Is there a path from candle to mirror bouncing off and striking any of the labeled points? This is Google form question K. The candle is here. Sure, why not? The candle is still holding a pillow out in front of themselves. There's a very small mirror located right there. Same plane, same angle, same along this board vertical distance, same angle, same everything. So just I've smashed all the mirror here. I'm angry. I don't like my reflection. A lot of self-hatred going on, and I smash the mirror everywhere right in front of myself and over there. And we've got some serious we've got some serious dissension here. I stand at the same location here. I am located, wow, that's not what I wanted. I locate myself here. I am the candle. There is only mirror in a tiny location. I ask you, is it possible for any of these points to see the image in the mirror? My question is there a path from the candle bouncing off of the mirror entering point, for instance, E? Yes, there is. If you cover a mirror, you restrict the places that can see a given object in the mirror. You do not remove just the parts in front of the mirror from the reflection. You just remove where can see that reflection. If I stand at E, I can still see the candle's image just as well. It's just I've taken away a path. D can no longer see the candle. It can see the reflection, can no longer see the image. Okay, I will have you do practice on this. You can see a reflection if there's a line that goes from you to reflection, from you to image, passing through the mirror, because that's a path that will have equal angle of instance and reflection. Let's see, I would like to test this out. Let's see if you guys get better on this now. Okay, we're done with reflection for now. Now we'll talk about refraction. Refraction is how lenses work. Refraction is part of how rainbows work. Refraction is how prisms work. Refraction is how lots of interesting things work. Refraction comes from light slowing down. When light goes from one medium into another, I should say, when light goes into a transparent medium, it may slow down. If light goes from a transparent medium into another transparent medium that is less optically dense, it can speed up. You can't speed up going into air, though. You can't slow down going into air. Unless you're very nitpicky and we're talking about vacuum. Whatever. And now I'm making things confusing. Let's get back to this. When a light ray slows down, it can change direction. This is refraction. If you go straight into a lens, if you go straight along the normal line, the perpendicular line, you don't turn then. You have to go in at an angle other than 0 degrees. Remember, 0 degrees relative to the normal. The law of refraction depends on the index of refraction, n, or also called the refractive index. And I want to check you guys again here. Suppose that light is only a third as fast in some medium. Let's see if this is clicking more. Google question n. L, V is 1/3 of C. Can you tell me the index of refraction in such a medium? If V is a third as fast as free space, not Google, David. Hmm? Wavelength changes. Yeah. Frequency has to stay the same. Okay. So we're still having trouble with this. No, give one more minute. And then we need to have discussions about fractions. Again, the question is solve for n if V is 1/3 of C. Not find V. I'm telling you what V is. V is 100 million. Frequency. Okay, so prisms splitting light into different colors is due to a subtle thing called dispersion, which is to say that different frequencies of light actually do travel at very slightly different speeds. That's a second order effect. That is a complicated interaction between the medium and the light. Wavelength n equals wavelength out. Will not shift. Will look the same. Yes. The way that the light actually interacts with your eye is a quantum process. An individual particle of light interacts with you. The particle of light carries an energy directly related to its frequency. The frequency has not changed, the energy has not changed, the color has not changed. Which molecule of the opsin-rhodopsin complexes, this is beyond my scope, I haven't taken this level of anatomy, I only know that there are molecules of various things detect the various energy levels. The energy level detected is directly connected to the frequency of the particle of light. There is no wavelength of a quantum of light. Yeah. Okay, so we're at 80% of the class. Here we go. 300 million divided by 100 million is 3. The best way to do this is, I don't know if your calculators are hindering or hurting you here. Let me think about this and let me talk to my wife about how to scaffold this for the 30 odd people here who are struggling. Index of refraction, I will tell you, for our problems, index of refraction, it is impossible to be less than 1. And if you're getting an index of refraction in the millions, you done did it wrong. Index of refraction for our purposes is going to be something on the order of 1 to 10. We are out of time to practice fractions, so let's go on to the foundational equations, which I will require you to do. Here we go. You want to find how angle the refracted ray goes when it turns inside the medium? Solve this equation. Yes, there are trig functions here. Sorry. N1 is the index of refraction in medium 1. Theta 1 is the angle that you are coming in at in medium 1. N2 is, you'll never believe this, the index of refraction in medium 2. Theta 2 is, you'll never believe this, the angle in medium 2. So if I go from light into glass, where I've got, say, n equals, I don't know, 1.5, from air, light equals n equals 1, I should erase the lines indicating glass because that makes it look like there's lots of rays. Let's have an angle come in at, oh, I don't know, 30 degrees. Here's my incident ray. I will draw the normal just for the hell of it. Is that right angles? I think that's right angles. Okay, so I'm saying that the index angle of incidence is 30 degrees. I challenge thee to find the angle at which the refracted ray comes out. Here is the refracted ray. Find me that angle. Plug into the equation. In your calculator, second sine is the inverse sine function. That's how you undo a sine. Google form M. Yes, Sabrina, vampires, as long as they are documented in Disability Resource Center, will be exempted from questions on mirrors. .00036 if memory serves. Is very small. I have a good question here, but I'm not I need more words to parse it. Someone asked, index of refraction when? Please say more and I will happily answer. If you're getting 0.34, convert your calculator to degrees mode. You're in radians. 0.34 is the right answer in the wrong units. Question asked, don't we need N1 and N2 for this? Bam, right there. Someone asked, could I explain N with more details? N is the slowdown factor for light. If I am moving at the global speed of light in a vacuum, N is 1. If I'm moving half as fast, N is 2. If I'm moving a third as fast, N is 3. If I'm moving a quarter as fast, N is 4. If I'm moving a tenth as fast, N is 10. If I'm moving at 1% as fast, N is 100. N is the ratio of speed of light in vacuum divided by speed of light in the medium. Piper, you can't see that? What? Really? Okay. Piper says we can't see N's in the Zoom. Can you see where it says refraction at the top left? That Zoom shows what's on my screen. Oh, you can? Okay. Yeah. Okay, good. Haneen, you're in radians mode. You're doing 30 radians. No. If I tell you degrees, put your calculator in degrees mode. If I tell you radians, put it in radians mode. Okay, so here's how I would set this up. I plug in numbers. N1 is 1. Theta 1 is 30 degrees. N2 is 1.5. Theta 2 is unknown. I'm going to solve for theta 2. First, I get the stuff away from sine. I divide both sides by 1.5. What is that? 2/3 of, I evaluate sine 30. I happen to know sine 30 is a half. Special triangles. Finally, I take the arc sine of both sides, which your calculator says sine -1. (19.5 degrees). Again, if you got 0.3 something, that's in radians, you need to use degrees mode. If I tell you degrees, if I ask for degrees, use degrees. If you're getting 15, then you're just dividing by the index of refraction. Sine cannot be canceled out. Those are not the letters s times I times n. That's a function. You have to evaluate the sine of something. Take the arc sine, inverse sine of something. And if you got 30, again, you can ask me a question, but I'm not sure where that goof comes from. Okay, there's one more slide. Sorry, last thing. Here we go. There's something called total internal refraction, which total internal reflection. I'll go into this more in detail when we're not, at the very last gasp of time. But I will tell you that the biggest that sine can get is 1. Sine of 90 is 1. You can't get more than 1 out of the sine function. So if I send light from an optically denser medium into an optically less dense medium and have the outgoing ray skimming the surface like that, if I come in at a steeper angle, it's impossible for any ray to come out. This is called total internal reflection. To find that angle, set up this equation. N in sine theta in equals n out times our maximum possible is 1, solve for theta 1. I mean, just algebra here. This is called the critical angle. It is the angle that will tell you you suck. No, sorry. It is the angle that is the maximum possible angle I can approach the interface, the surface, the boundary at, and still have refraction. Any bigger than this, no refraction, all reflection. This is how fiber optic cables work. As long as you shoot the bits of data in fiber optics at a shallow angle, less steep, steeper relative to the output than this, you're guaranteed that the fiber optic cable will not leak any light out. All the light will only appear on the other side of the fiber optic cylinder. I will review this next time because we're saying this at the very end. We're done for today.
Beautiful sunset window where we have both reflection and